Welcome to part 2 of Mind the Gap, where we're going to continue having a look at these ignition coils. So here's the ones we're looking at, here's the new one and here's the defective one. Sam wrote in and asked me if we could have a look inside this coil. He said, can you open it up? And I think that's a great idea, Sam. I've got to admit, I've always been interested to see what's inside these ignition coils. I know that it's full of oil and the basic topology is going to be some form of auto transformer, but I've got no idea what they look like inside, so we'll go and do that. We'll section it and drain the oil out and have a look-see. So here's our ignition coil that I brought out to the garage, and I don't know if you can hear that. Can you hear that? Well, these things are full of oil, so I want to drain that out. Oh dear, I just managed to pour that all over my bench. And I'm going to actually try and flush it out, I think. So the way that these are manufactured, it's a bit like a tin can, and the end's obviously rolled on, crimped on, so I'm going to try and take it apart the same way, I think. You know, I actually think it might be easier to cut all around it on second thoughts, because it is only very thin metal. It cut quite easily, so I'm going to get the saw in again. So it is all a bit wibbly wobbly now. Oh, there we go. If you're watching this, it's a one-time job. So we've got the coil open, and it came wrapped internally in this well, it's kind of brown paper that if you've ever seen big industrial transformers, you'd be surprised to know that they actually do have quite a lot of paper in them that they use to insulate the windings in different layers. So we've taken the little paper bandage off it, and we're presented with, well, I can see where the weight is. It's in this bobbin of, well, copper wire effectively. And I'm guessing there's quite a bit of wire here. Primary winding here, which is made of I was going to say relatively thick wire. It looks as though that's probably about 0.5 millimetre thick. And then we've got a secondary winding, which is, if I just pull it apart, is inside. And this transformer, which is an auto transformer, it's got an iron core, which of course is typical for a transformer again, but the iron core is made up of not one piece of metal, lots of little separate pieces of metal. I can just pull them out, can't I? Pull them out like that. So these laminations that were sitting in the centre, interestingly enough, they were also making contact with the output from our ignition coil, the high voltage side. So they're actually using the laminations not just as you know, something to help raise the magnetic flux for the transformer action. They're actually also using these as probably some form of conductor, although it looks like maybe there's a separate strap here. Interestingly enough, I can see some staining on the side of these laminations. I wonder if that's an indication that this has been a bit hot at some point. I've got no idea, it might do. But here are all the laminations, and of course they're not a solid lump, they are separate laminations. Look, I can fan them out. Lots of strips of very thin and no doubt very sharp metal. Let's just put them on one side. So we've got the thicker wires here, which are the primary winding, and then we've got an inner core, which is a secondary. And look, can you see the little tail coming off the secondary core there? So we've got this tail here, and this reconnects to the two 12-volt input terminals. So what we've got here, we've got an auto transformer configuration. I wonder how much wire there is on here. Let's shall we find out? In fact, let's just disconnect this, we don't need it now. 1, 2, 3, 4, 33, 34, 92, 93, 94, 95. Right, so we're at 140 windings so far, and I can just start to see the end of it. So 141, 2, 3, 4, 5, 45, 46, 47, 49, 50. That puts us now at 200 windings. Oh, God, got this stuck around my finger now. Oh, I'm trapped. Come on, get off. Gonna be trapped here forever. What did we say? Said that was 200, 201, 202, 203, 204, 205, 206, 207, 208, 209. Okay, so we've unwrapped that now, just left with the bobbin. So 230 secondary windings. Now, if this stuff wasn't covered in transformer oil, it'd be quite good to keep. It seems like a really useful enamelled wire. So maybe if you're an amateur radio person and you want to put a long wire outside your house, if you don't mind messing with the oil and stuff like that, perhaps you could do worse than finding an old ignition coil somewhere and unwinding it, and you probably, I don't know, there's quite a lot of wire there anyway. Bonk! Nearly fell on my arse then. So looking inside the can, it does look as though we've actually got a little bit more magnetic shielding, some more mu metal. I wonder if I can get that out. Oh, it's in two pieces. So there's one piece. Another one. God, it keeps going. It's like with a magic trick where you know, they keep pulling sponge balls out or something. There's still some more in here. I think that's all of them. Yeah, that's all of them out. So I've got a couple of those sheets of material here that we've just removed from the casing of the coil. And again, it's made out of the same, feels like the same type of material as the laminations are made of. So again, this will be made from what they call mu metal. And mu metal has got very specific characteristics, which is to do with, I think it's to do with permeability, which again is the ability to be magnetised. There's also other characteristics about permeability, which is to do with not having a magnetic memory, because you need metals which you can magnetise and then demagnetise quite quickly. So those metals, it's a special alloy which they tend to call mu metal. Now of course they could have made this as one single sheet, maybe formed a tube out of it, but the reason that they didn't do that is because if you'd have made it as one solid piece like that, you would get currents induced in this shell in the tube. It would induce currents in it. They call them eddy currents. Now the eddy currents don't do anything useful. They actually end up being just wasted as heat within the transformer. So these eddy currents just produce a type of transformer loss. They don't do anything useful. So if you actually break up the ring into lots of separate pieces like that, it helps to stop those eddy currents from forming and makes the transformer much more efficient. So the only part we've got left now is this secondary winding, and these are going to be much thinner wires. I don't know if we'll be, oh, in fact they're so thin I've just probably broken one off. Got that on the floor, we don't need that anymore. So looking at this secondary winding, I can clearly see now this burnt patch. So that's why our transformers actually failed. The windings have shorted together and they've actually burnt, because this is covered in layers of paper. The way that you wind these high voltage transformers, what you've got to be very careful is you can get a high voltage flashover from the high voltage side of the coil. Well, let's call it from the inside of the coil to the outside. So you'll have like a low voltage on one side and the voltage gets higher as you move out from the centre. But what can happen is you can get a flashover between one side of the transformer from the high voltage to the low voltage side, and when you get that flashover, well, again, it can damage the transformer and cause all kinds of nasty things to happen, burns the insulation. So what they've actually done is, so you lay down a few windings, you put one layer of windings down, and then you use some insulating paper, and again, it's just, literally it is, it's just paper. And then they put another layer of windings down, and then another layer of paper. So if you look at this end on, you can see that there's layers of windings and also layers of paper. But I can clearly see this is where the transformer, this is where our coil has failed. Can you see it's all black and stained there? Really not that much to see apart from just the burn is evident. So it does look like whatever damage occurs seems to have happened on this side of the secondary winding, because this paper's quite soft on one side, but this side it's charred. Well, I don't think there's much more we can say about this. You know, it's lots of very, very fine windings. I'm not going to, certainly not going to attempt to unwind this and count the number of turns on it. We would be here, I suspect, all year. But I suspect there's probably many hundreds, and more likely many thousands of turns on the secondary winding, because of course you need a ratio. You need a ratio between the primary and the secondary. So if we take the idea that you put 12 volts in and get 40,000 volts out, I'm sure you can do the maths. I can't do it in my head, but 12 by 40,000, that's going to give you the number of windings we've got on here. That's going to give you the transformer ratio. And maybe I'll work it out when we get in the house with a calculator, but it's going to be a significant number of windings.
Just because I'm presuming that I could be kinda human if I only had a...
There you go, the Tin Man's pubic hair. Yeah. Well, as you guys probably expect, I do enjoy a little bit of destruction, so it was certainly very interesting to have a look inside that coil. So Sam, thanks very much for suggesting that, it was interesting. Well, another of our subscribers, Scott, better known as the Deaf Pom, also got in touch. Now, it was Scott that asked to take a look at the primary current in our ignition coil here. And what he suggested is that we could use a current shunt to look at that. So I think it's a bit of a coincidence, really, that we've never really talked about current shunts before, and then we did in the battery charger video just last week. So here's a big current shunt, which is a fairly high powered one. So this is a 100 amp one, which is similar to the one we used in the battery charger. So this has got printed on here 100 amps equals 60 millivolts. And the way you actually use these, you would connect this in line with the supply, and then you will measure the voltage across it. And all it is, it's a very low resistance resistor. So what this is telling me is if it's got 100 amps flowing through it, you will get a volt drop of 60 millivolts, and that's all a current shunt is. It's nothing more exciting than that. It's just a resistor, but it's a very low resistance resistor. So this current shunt I've got here is actually quite a big one. It's 100 amps, and the way you'd probably use this, we'd probably use what they called low side sensing. So we would put it in, rather than put it in the positive side of the circuit, we'd put it in the minus line. So we'd disconnect the wire from here going into the minus side of our coil, and in its place we would install this current shunt like this, and then we would connect the wire to this side. So the current would flow through the shunt into our coil, and then what we could do is we could connect a voltmeter across here, and that would basically tell us at any time what the current was, because you can basically, if you know how many millivolts it is, you can predict how many amps it's drawing. It would probably be more interesting, of course, though, to connect an oscilloscope to it, because it's always more interesting to see, well, this is not a static DC current flowing through it. As we turn the coil on and off, you will get current transients. So the thing you really want to look at is, you'd want to look at this on an oscilloscope, really. You'd learn a lot more. Now, depending on the current that you want to measure, as I say, this is a 100 amp one, they actually make more specific current shunts. So I've got a few here. So here's one that says, here's quite a small one. So 300 milliamps, 75 millivolts. So if we put 300 milliamps across the current shunt, it'd have 75 millivolts. What have these others got written on? Got a 3 amp one here. And again, we've got 2 3 amp ones, and what somebody's done in the past, probably me, I've soldered them together. So I probably wanted something that was 6 amps. So what I've done is I've taken 2 3 amp current shunts and I've soldered them together. There's another 300 one. And here's one amp equals 75 millivolts. So these are what current shunts look like, and depending on the magnitude of the current that you want to measure, there are different sizes available. Well, we certainly could wire in one of these current shunts and use it to take a current measurement, but it probably wouldn't be my preferred choice. And the reason it wouldn't be my preferred choice is because large inductive loads like this can produce quite high voltage transients, or would you be better to call it a back EMF? When this coil actually de-energizes, when we turn the current off to it, it tries to maintain the constant current through it, and the way it does that is probably more complicated than we need to do, but the way it tries to maintain the current through it is by increasing the voltage to try to maintain the current through it. And it's for that reason why you get a bit of a spark across these contacts of our relay, and it's what the capacitor's designed to prevent. So basically, because it's an inductive load, you get a spike, you get a back EMF. Now, I'm always a little bit cautious when I'm taking measurements on inductive loads. I prefer not to connect test equipment directly to large inductive loads, and the better way to take measurements on inductive loads is to use something called a current clamp. Now, back in the day, I remember buying a Tektronix current clamp probe, and it was several hundreds of pounds, very expensive bit of kit. And I'm going back quite a few years, and the specification wasn't amazingly high. So I have got a Tektronix probe, but unfortunately it's buried in the hoard somewhere, not sure where it was. So I thought I'd go away and buy another one. In the last few years, things have really changed. I've gone away and I've bought this Hantek probe. Now, don't know if it's any good or not. I guess we're going to find out today, because I'm going to try it for the first time. So I don't normally do unboxing videos, do I? But yeah, there's an unboxing video. So there's the box. They do a few versions of this, and I've got to admit, I've actually gone away and I've bought two of them. This is the version that I've got. It's up to 65 amps, which I thought would be perfect for measuring the primary current to our coil. But they also do some different versions of it. They do this one, which is the CC-65, which amazingly enough goes up to 650 amps. And they also do a probe which goes up to 1100 amps. Now, I'm not going to say that these items are cheap. Whenever I call something cheap, somebody always goes, "Oh, that's not cheap." This was £70, and for a current probe, that is amazingly cheap. Because when I bought them in the past, it'd been several £100s. I don't know what the performance is going to be like. We'll have to find out. I've got to admit, the printing on the box and stuff like that is good quality, so it's not particularly cheaply looking. Got some instructions there, which unfortunately we might have to read. Ooh, excuse me. So this is the part of the video where I tell you all about specification, how good this Hantek probe is, like I actually know anything about it. I know bugger all about it, I've just bought it. Here's some instructions. I'm not going to read them at the moment because I never do. I think we need some batteries. It definitely feels a bit light, so let's find some batteries. Okay, little screw. I don't really like screws on battery compartments, but it's got one. But the plastic body here has got like a little brass insert in it, so it's not like the screw is just a self-tapping screw. So that's a nice bit of quality feature. So we need a 9-volt battery for this. Now, one of the things that I think is interesting about this current probe is the fact that it's an AC and DC probe. Well, actually, that might be a bit of a... Okay, that's not great. This terminal is a little bit loose. Okay, let me see if we can give that a bit of a squeeze. I'm afraid I lost my train of thread. Yeah, one of the interesting things about this is that the probe is an AC and DC probe. Now, a lot of these current probes only actually work on AC, but this is a DC one, so I think what it has inside... That's still a bit loose. I think they actually use a field effect transistor rather than you know, like a coil technology. I'm not exactly sure. That's a bit bare. It could be better, that. All right way around, does it matter? Okay, that should be alright. Now I've just had a cursory glance at these instructions, and unfortunately they seem to bear absolutely no resemblance to the actual device that's been shipped. So here's a front panel. We've got a selector switch here, a range selector, so at the moment that's in the off position, and then we've got 1 millivolt equals 10 milliamps, or 1 millivolt equals 100 milliamps. If you want to measure a big current, you have to put the range switch to the top, 1 millivolt equals 100 milliamps, or if you're measuring a much smaller current, you pull it down one to the first notch, if you like, and that's 1 millivolt equals 10 milliamps. I don't know what position we'll have to be in, we'll have to give it a try. Also got an off button, we've got an LED power indicator there. And the instruction manual talks about having a zeroing adjustment. It talks about a turning knob that you need to turn. Well, there's a button on here, but it is a push button. It doesn't appear to turn. I'll tell you what, let's find an oscilloscope and plug it in. Now, of course, I do know I should tidy up when I've got guests coming, but I'm afraid I'm that used to having you guys around now that I don't make any effort for you, do I? So you're going to have to put up with my messy workbench. So I am sorry about that. So there's our scope. Let's turn that on because our old TDS 2022B does take an age to boot up. In fact, the old menu on it is, it's like as slow as a glacier, I'm afraid. Right, AVO, that's going to be handy to check our current, a little bit of a reference meter there. Oh, we need another wire. And we need some current. I think we'll just use the power supply. And let's set this to give us a test current of, let's go for something like about 1 amp. Well, I'm sure that you know this, but whenever you're using a traditional analog meter like this old AVO, they are designed to be sat flat on the bench, and you do lose some accuracy if you stand them up like that. But I am going to stand it up like that purely from the point of view of getting it on camera. So all I'm going to do now is I'm just going to take our power supply and I'm going to connect it in parallel with the ammeter, so I'm effectively shorting out the power supply, and hopefully my power supply is going to current limit rather than just exploding. We'll find out. Whew, got away with that one. Anyway, my needle has gone full scale. It's actually gone above 1 amp, so I think we could do with trying to trim that back. So I'm going to open up the clip on our clamp meter just by pulling the little trigger on it, and then we slip the wire through, and hopefully you can see it's gone up by 1 division, which is 100 millivolts. Now, the way I'm guessing this will work is, of course, the number of divisions of deflection is proportional to the current going through the clamp meter. So if I just reach over and I'm going to increase the current on the power supply, I'm going to let that current limit at 2 amps. That should go, well, it should go up even higher. It should go up to there. So about 1.5 amp. And now we're at 2 amps. So we've just proven now that the millivolt output from the current clamp is proportional to the current running through our thick red wire here. Now what we could do is if we actually just switch the power supply leads over, rather than getting the current running in one direction, it's going to run in the other directions, which should make our cursor here, our trace, so it should deflect in the opposite direction. So that was the 0 centre point there. So if we just turn the power supply leads down, we should have minus 2 amps, so that should put the trace down there. So I'm just going to try that. So disconnecting our current now. Reconnect. And there we go. So it's gone just over 2 divisions again. So the current is going in the opposite direction. I'm absolutely amazed by that. As I said, I've used current clamps in the past, but I've always used them for measuring on great big AC motors. I've never had a current clamp that would work on DC circuits like this one is doing. What this must have inside it, it must have some kind of sensor or probe which is sensitive to the magnetic field given off by this wire. And that's what I think it must be. So I'm guessing it's maybe some form of a Hall effect transistor, but I'd be lying if I said that I knew. I don't know what technology it uses, but certainly it seems to work. Now I did notice when I first plugged this in for the first time, I had a little bit of an offset on there. In fact, let's just turn it off again and switch it back on. There's a tiny little offset there, and I think that did go away when I pressed the 0 button on it, which is this one. Yep, it did. It zeroes it out. Sometimes you've got to press it a few times, but that zeroed it out. So that seems to be working. Now, of course, the other thing to note with your current clamp is if you actually put the current clamp on the other way around on your wire, you'll get a different reading. So let me just again show you that. So that's on that way, but if I actually turn the clamp round on the wire, it goes up. So kind of not a problem, just something you've got to know when you're using current clamps. So far, my first impressions of this Hantek current clamp, it's £70. I've only done very minimal testing, obviously, but it seems to work really nicely. It feels like a quality product. The plastic case is lovely. The clip is very firm. It seems to work. Don't know what frequency it goes up to. Well, I do know. According to the manual, it goes up to 20 kilohertz. I think this is a really, really useful bit of test kit. An absolutely brilliant value for the money. So thumbs up to Hantek there with their CC-65 current clamp. And if you want to send me some free test gear, Mr. Hantek, I'm up for it. Well, as you can tell, I'm quite excited to be playing with my new toy. So we tried measuring 1 amps and 2 amps, but let's try something kind of on the opposite side of the scale. Let's just try measuring 10 milliamps, which is going to be at the lower end of what this thing's designed to do. So what I've done is I've turned our power supply up to 10 volts, and I've got a 1k resistor here. So that basically means that 1k across 10 volts, it's going to give us 10 milliamps, isn't it? Now the lowest input voltage I can go down to on this scope is 2 millivolts per division. So I'm guessing for our 10 milliamps current, we should get about half a division of deflection on the trace. And we seem to get that. Well, it's not quite, a little bit under, but I'm still quite impressed with that. I mean, to be able to measure something down to 10 milliamps with a contactless measurement tool, I think that's pretty good. So I'm going to reconnect our resistor now. Not quite half a division, and let it go. Well, we've seen a very low current measurement. Let's see a high current measurement. And actually we were doing DC before, so let's do an AC measurement. So you can see we've got a nice AC waveform there, haven't we? And you can see it's got a positive half cycle and a negative half cycle. And of course the current that we're measuring here, we only want it between the zero crossing point and the peak. So that's 500 millivolts. So according to the range that we're on, 1 millivolt equals 10 milliamps. So that would be 500 times 10 milliamps. So that's so the current peak there, the positive current peak is 5 amps, and the negative current peak is 5 amps. And I'm guessing that's about right for this radiator. Unfortunately, I can't really turn this radiator. Oh, for fuck's sake. Well, I hope you don't mind, but we took a little bit of a segue there into our Hantek C-65 current clamp. But you know, sometimes you just have to slap it out on the bench and play with it, don't you? So back to what Scott actually asked for many hours ago. Let's just clip this in with the positive lead, and we're going to connect up our supply to our coil. So here's our current waveform, and it's about 450 millivolts, maybe just under, maybe 420 millivolts. So it's 420 millivolts from the bottom to the top of the waveform there. And if we just look at the setting on our Hantek probe, that's on the 1 millivolt equals 10 milliamps. So it's about just under 4.5 amps between the top and bottom of our waveform there. So a few things to point out. This is where the coil gets switched on here, and you can see that the coil gets switched on, and then it overshoots, and I'm sure if we zoom in on the scale there we'll find we've got some ringing. But I think what's more interesting is if you actually look at where the coil switches off, you can see this curve here at the bottom. You can see it's a sharp edge there, but it's a curve there, and that actually shows us that's the capacitor there doing its job. So effectively, when we switch the power onto the coil, the capacitor is switched out of circuit, so it doesn't do anything to limit the rise time. So we get ringing, but you see there is no ringing on the fall here, and that's because the capacitor here is it's just rounding it off. We're getting some current flow, so it's actually slowing down the rate of change. So we get ringing on the rise of the waveform, but we don't get a ringing on the fall. So I've just zoomed in a little bit on our rising edge, and there's the ringing I was talking about. But if we actually move over and look at the falling edge, so you can see the falling edge of our current waveform here. It's not sharp, it rolls off very gradually, and that shows that that capacitor's doing its job. It's actually stopping, it's slowing down the rate of change of the voltage falling across our inductor here, across our coil primary. Now you can see on the AVO meter it's actually displaying about 2 amps. Well, you might think, oh well, that's not right, is it? It's only showing 2 amps, and we've just proven with a current clamp meter that it's actually 4 amps. Well, of course the AVO meter's averaging. So quite rightly, when our coil is charging up, it's drawing 4 amps. But when the coil's switched off, it's drawing no current. So if we were to average this, 4 amps, nothing, 4 amps, nothing, the average current, of course, is 2 amps. And if you remember, I did say in the previous video that sometimes there is still some utility in using these old analogue meters. You know what, I think for today, that'll do. So until next time, thanks very much for watching, and I hope to see you again very soon. But until then, bye bye for now.